Yesterday I mentioned about VCOs named source coupled VCO, but I wrongly drawing a picture topology without thinking a bit. So I rethink and rewrite the drawing of the source coupled. Source coupled name is dangerous word because this is drain, but this is source drain coupled. I like drain coupled. If source coupled, it never oscillates. And the VCO made by controlled ID, two ID, same ID, symmetric ID, which knows is VA and VB. Between them, a capacitance is connected, and this capacitance is discharged alternately, or in an alternate fashion, discharging movement around the capacitor oscillates with this coupled switch. This is just switch and small resistance, on resistance, as small as possible. And this is diode connect current source, and the VDD is movable, supplying ID or 2 ID alternately for discharging C. I call this M1 and this M2. When this is on, this is off, and this is off, that is on. And first, M2 is on, and M1 is off. VA node is discharging current. VA node discharges. Current is in this direction and also in this direction. So this current is, this was off, this is ID, and this is same ID. So this needs to draw 2 ID in this time, in this decade. This is VA. VA is discharged around this delta T decade. And alternatively, like this fashion, dotted line is for voltage V of node V, and this 2 delta D equals output alternating period, and F equals 1 over T, 1 over 2 delta T. Within delta T, VA and VB is alternatively discharges, and while this is M2 is on, this current flow this switch can draw a current of 2 ID, and when this M1 is off, this voltage is going to, because of delta T and T is very small enough to this node to VDD, because which means this N channel MOS is in sub-threshold level. So this is around VDD minus VTH, this gated VTH. VGS equal around VTH. So this is around VDD minus VTH. This is out, and this is outbar. Outbar going around VDD minus VTH roughly looking at in a short this fast movement period. Of course, this is going upward for the time going. Around the time going, VDD minus VD2 upper voltage, but a very little variation among this decade. So approximately outboard is VDD minus VTH when M1 is off, M2 is on. And M1 is off, VA is high impedance and to be discharged to here to here. How much VA can be discharged is determined by when this is on. And V out when this is M2 is on, going to where? V out is need to V out need to less than VTH with VTH from VDD minus VTH or outboard, because outboard is a gate of this. Outboard is gate of this, and this is on. V out equals VB, and VB to outboard is larger than VTH, more than enough enough to this M2 on. And outboard when VTH minus VTH is out equal out B. When out equal out B shorted, this is VV V out, nearly out, and this is less than VTH. So this is VDD minus VTH minus VTH, which is VDD minus 2 VTH. When this in this decade, out going to VDD minus 2 VTH, and outboard is off voltage of VDD minus VTH. This is weakly inversion area. This is a saturated area. Because out equal VDD minus 2 VTH here. Enough on and enough on. VB equal less than this. VB equal on this. This is on. And when VA equals out minus VGS of M1 is larger than VTH or equal VTH, M1 change to state its state from off to on. So, and out this time going to VDD minus 2 VTH 2. This is off, M2 change to off, M1 on because of this, and M2 off going to off, this going to VDD minus VTH, and M2 this source and channel going to the operation area of weakly inversion area, weakly inversion of operation area, and very, very, very small current and almost off. And this time out is going to VDD minus VTH dotted line next time. At this point of at the edge of this point, VA is going to this is VDD minus 2 VTH and this is VDD minus 3 VTH. Less than VTH, equal VTH, less smaller VTH, smaller with VTH. So this least minimum voltage VA equals VDD minus 3 VTH, nearly this. And at this time the switch is changed, and this switch is on, and this is going to V out bar. Out is going to this time VDD minus 2 VTH. On the other hand, out exchange, and the 2 VTH going to be from VA. VA equals first VDD minus VTH 3 VTH minus 3 VTH to 2 VTH plus VTH pushed up. So from here to here, this steady state, because M1 is off this time, M2 is off this time, M1 is on this time, and this is on, and this is on, and the steady state may, and VB start to discharge. VB dotted line start to discharge. VB also at this moment, V is pushed up, and VB in switching moment is high impedance, and VB also pushed up. There's no current in this small moment, fractional moment. This is push up, both push up by VTH, going to VDD minus 2 VTH and VDD minus VTH respectively. So the delta V to peak voltage of V and VB equals delta V equals 2 VTH. VDH minus 2 VTH is a steady state point when switch is on. And this, and the ID discharges C with delta V divided by delta T, which is 2 VTH, and 2 delta T makes this output frequency period, this T, capital T, so delta T equals half T. So the T equals 4 T equals ID 4C VTH. Ready? Q equals CB, I equals C dB dt, 2 delta VTH, and IDT equal 4 VTH C over VTH over I, and TT over T, and T divided by ID. And so the frequency F equals ID over 4C times VTHN. Okay, at this frequency output oscillate from peak to peak with 2 VTH. 2 VTH at peak to output is VTH. Peak to VTH from VDD minus 2 VTH to VDD minus VTH. Off point, on point. And that's all. So to control this VCO linearly, we make linear voltage dependent ID. We need to make linear voltage control ID current source with this topology like this. P channel diode connected, current mirror to another P channel, going to this, and this is V count, V sub count. Actually, V count is like here, and regeneration, animals for regeneration, resistance, regeneration resistance, degenerate resistance RD needed, because this is quadruple dependency with V count. V count, these are when RD equals 0, like this. We need more of a linear area controlled by V sub control. We can't control the ID linearly when utilizing RD for the degenerating of the animal's current source. And this is mirrored to supply the bias of this N channel. The most simplest control voltage, control current sources are made by this topology. We easily come to in your minds. So this is a current controlled, voltage controlled, current biased, source coupled, or drain coupled voltage controlled oscillator. The swing of output is peak to peak of VTH, and alternating discharging node of VA and VB is peak to peak of 2 VTH. Very small, so we need to amplify the VTH to rail to rail voltage of VDD using like this buffer, differential voltage buffer, maybe like this output is connected VDD, P channel, diode connected, and this is output to buffer inverter, which is enabled to load capacitance, and another side of the differential pair, there's a V reference around VDD minus 1.5 VTH within around here in intermediate voltage of high and low of the output swing, and bias is self-biased to accelerate the node C transition from VDD to ground, rail to rail. When this is high, this is on and this is off, and this is going to high and this is off, and this is pulled down from here to here, and this is off, so this is nearly VDD minus VTH, this is very fully on, and this draw a big current enough, and this pull down is first. And when this is low, this is on, this is off, this is off going, this off going to release this voltage, this off, and why? But this is on, this is does connected, but it can be some pushing current, draw current. This is off, a little bit off, but this can this is in between the VDD, and this is on more than VTH, and this current is able to current, but this gate voltage can pull up this node fast enough, and so this pull up pull down movement is like this, accelerated, and small VTH peak to peak voltage referenced with VDD minus 1.5, around minus 1.5 VTH, compared by this self-bias differential amplifier makes it exchange to rail to the rail voltage, and with inverter enough to load capacitive load to drive we can generate the rail to rail oscillating output, rail to rail of frequency F. When F 1 over F equals 4C times VTH of N channel divided by this ID bias. Control ID is defined by V control linearly, approximately in a linear range of both V sub C and T, V sub cont. So the frequency is a function of linear function V cont in some V voltage range, in some minimum to maximum frequency range. So we can design with C and process VTH and control current VID. The VTH is process process variation on chip variation and temperature variation. So control voltage can be cancel the variation. So it depends on the control linearity of locking the frequency with this VCO using type 1 and type 2 PLL. This is a simple intellectual property I've never met, but it's a little bit difficult to understand, but step by step we can understand the movement if it is designed correctly. But overhead is very limited with VTH if VDD is small. So usually VDD is around 1.8 volts, so and the VTH is 0.5 to 6.6. It's possible to generate the pulse from this topology, but let's calculate yourself how many frequency, how much fast can this operate. You need small capacitance, small VTH, large ID. For small period, for higher frequency of this VCO. Are there any point commented must be commented here? Out burr on and off alternating discharging movement of capacitance via node via VCBB, and M1 and M2 used for switch. L is smaller, W relatively large, and current drive connected NMOS or PMOS, more effective and enhanced overhead drive, or in a first looking at this topology, it's difficult to imagine the oscillation movements of out and out bar, because it's simply latched to one condition seemingly, but alternating discharging movement happens using adequate capacitance between B and BB. It's just a little bit difficult to come up with this idea. Just as it is, like CMOS textbook by Jake Baker. As it is running step, you can modify and enhance this topology in some way or another. But at this time, I don't I don't commit so strong for the for designing VCOs. So next, type 1 PLL response is evaluated like following this textbook, Lazab textbook, and step forward to type 2. Type 2 is interesting compared by type 1. Looking at root locus movements, or with respect to changing the feedback gain, type 1 and type 2 response of root locus with respect to feedback gain is very different, and the latter is very useful, seems very useful. Faster, stable response is supplied by type 2, so many people use type 2, must use type 2 PLL, charge pump PLL. And next time, considering type 1 response and going to type 2 PLL. And finalize the basic PLL study for my English exercise, daily, not daily, weekly exercise. This is source coupled VCO represented, examined by me, by myself, just a little bit, without applying any numbers. So I don't know if it actually happens, how much current needed, how much capacitance needed. Other restriction there, I don't know this time, at this time, and I don't care. for the example, just example used in CMOS textbook.